Welcome, my friends. We are going to start today by talking about retention in GC. Retention in GC, and what it is that causes different analytes to interact more or less with the column and therefore come out at different retention factors. So here's what we already know. I told you last time that the mobile phase is just a carrier gas, right? It's not involved in retention. What we did see last time is that it can, the selection of the mobile phase can influence peak efficiency or band broadening. And we framed all of that around a discussion of Van Deemter and how Van Deemter changes with different mobile phase selections. But it doesn't play a role in the factor we're going to talk about today, retention, how long something stays on the column. So generally speaking, and the thing that we learn if we learn about GC as an undergrad, um, it's that retention is proportional to boiling point. This sets up a really strong analogy to distillation, right? Things that uh, boil at higher temperature will stay in your distillation flask longer, while things that boil at a lower temperature will get out of there pretty quick. And that's true, all things being equal. If we compare two analytes that are extremely similar in structure and are on the same column, absolutely their retention order will be in the order of boiling point. But it turns out this isn't the whole story, right? That's not the whole story. And that's because we're not just taking like a pot of analyte, sticking it on the stove and boiling it. We're not just talking about its vapor pressure here. Um, that's because there is retention forces or interactions that lead to retention um, exerted by the stationary phase, right? The structure of the stationary phase where these things are going to condense into and essentially be dissolved into, very similar to liquid chromatography, is going to exert intermolecular forces on those analytes. The stronger those intermolecular forces, the harder it's going to be to boil these things off and get them volatilized. So two molecules of extremely similar structure are going to have the same kind of intermolecular forces, and then it's going to come down just to their boiling point. But the bigger question is, how do those molecular structures affect this retention? Or in other words, how does stationary phase affect the retention as a function of the structure of the molecules? Um, so I will say this, I'll say that, so obviously the idea here is that we're adding thermal energy to try and get these things volatilized into the gas phase, but we are also fighting with the intermolecular forces that lead to retention. That means that selection of the stationary phase can be used to tune selectivity of the chromatographic method, right? It can be used to make sure that a certain class of molecules have stronger retention than, say, a different class of molecules. So let's look at a couple, before we talk about how we're going to characterize this retention, because we have some quantitative ways of doing this. Let's look at the molecular structures of some common GC stationary phases. I've put these into three really common categories and then kind of a bucket for catching everything else. So four categories. The first one, we'll call these just hydrocarbons. So these are stationary phases that are made just entirely, well, like I said, of hydrocarbons, and they come from sources like petroleum grease. This is an old school stationary phase. One that we're going to talk about a decent amount a little bit later, squalane. So this is a saturated C30 molecule. You can look up the structure of squalene. It's a little bit branched, but it's basically a saturated C30. Okay, so another really, really common class, probably, at least in my experience, the most common class, are these polysiloxane materials. So these have a general structure that looks like this. It looks a lot like what we see in, say, silica particles for liquid chromatography, and they have these R groups hanging off the edge. And these R groups, they can be things like methyls. They can be they can have phenyl structure. There's actually a huge variety of different structures that can dangle off the edge. I'm just showing you some of the more common ones. Cyano structure. Some common motifs that we saw when we were talking about um, stationary phases in liquid chromatography as well. So let's define a few of these just so we get a feel for how these work. A really common one, OV1. And OV1 is where R is 100% CH3. So if you're following, that means that OV1 is a material called polydimethyl siloxane. I haven't put the N here to indicate that that's poly. Um, PDMS, if you've ever used PDMS, we use it all the time in our microfabrication materials. I know some folks who are interested in gas membranes have probably used PDMS. There's probably 1,000 other uses for PDMS. Straight up, PDMS coating the walls of a capillary makes an OV1 open tubular GC column. There are a lot of these OV structured or classified. I think it's a commercial, like a trade name. OV17 is very common. This is where we have 50% CH3 and 50% phenyl structure. Okay, let's give one more here. XE30, I think. XE30. These just have these peculiar names, I think, because they originate from being trade names. So I think this is 50-50. I think it's 50-50 cyano structure and methyl as the R side groups. Okay, so a fairly common motif here. You can think about to what degree these are substituted, and that basically defines the entire class of these polysiloxane materials. There's another really common class of stationary phase materials in GC. These are polyglycols, mostly polyethylene glycol. So predominantly we're talking about this right here. Sorry guys, not a polymer scientist here. To kind of keep looking back at where we put these brackets. Yeah, I think that's right, polyethylene glycol. And these go by the commercial trade name Carbowax, and I'm sure there are 1,000 other trade names that are based on this material, and the different Carbowax materials are essentially just based on the different sizes of these polymer chains. Okay, and then the catch-all category that I said there's just other materials. So we have various like hydrocarbon functionality, right? So various functionalized hydrocarbons. We'll see how we might design some of these functionalized hydrocarbons a little bit later when we talk about how we quantify the properties of these materials. There are chiral columns in GC, and these are very much like the Perkel phases that we talked about in LC. You get exotic materials like liquid crystals, and other weird things. There's no shortage of research in the area of weird stuff to go in a GC column. Okay, so here's a good question. How do we compare all these? What do we do to understand how these things differ and how their performance might differ in a method development, a GC method development, or a GC application. So we're going to need to talk about two related concepts here in order to get to a place where we can numerically, quantitatively compare different stationary phase materials. The first one we're going to talk about is called the Kovat's retention index. So in general, a retention index, there's lots of these. You'll find lots of different things classified as retention indices. A retention index is an approach to describe the retention of analytes or model molecules on a column in a way that is normalized for variables that change from lab to lab, right? Some way to kind of universalize how things are retained on a column. You see them all over LC as well. It turns out this one has been an extremely useful and widely adopted retention index used in GC, and so it's the only retention index we're going to talk about. We'll see a little bit later why retention indices are a little harder to do in LC. So to get a Kovat's retention index for a specific molecule being retained on a specific column, the first thing you do is you run a chromatogram of normal alkane standards. Okay, so we're gonna get a chromatogram. It's gonna look something like this. This is time, of course. This is signal. That's what chromatograms are. We're gonna get these evenly spaced peaks. Okay, so what do we have here? These would be something like, so N-alkane standards, this would be something like, you know, let's see, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So this would be something like C7, C8, C9, C10, C11, C12, etc. Right? This, by the way, is an example of something that's used a lot in chromatography called a homologous series. A homologous series is basically if you take one class of molecules, in this case the class is N-alkanes, but you could imagine, I'll give you another class that we could do this with, something like, you know, gosh, alcohols, right? So like methanol, ethanol, propanol, butanol, right? This is a series of molecules, standardized molecules in structure that all differ by one carbon or in other words, one CH3, right? So homologous series is some functionality that you have a full set of standards. They all differ by just one carbon. Okay, so you have this homologous series. That's the first thing you do to get a Kovat's retention index. The next thing you do is you take the same homologous series and you are going to spike in your molecule of interest. So whatever that molecule is, it's going to pop up here as an extra peak. Let's say it comes up right here. So that dashed peak, that's your molecule of interest. It's the thing you are trying to produce a Kovat's retention index for. We're going to call C10 our leading peak. So C10 is our leading peak. We're going to give it the abbreviation N. And N refers to 10 for C10. That makes C11 our trailing peak. In other words, we are just defining the two peaks that bracket our analyte of interest, and we'll call this N plus 1. Okay, so our leading peak, our trailing peak, we're going to define those as N and N plus 1. Here's our analyte of interest. In the math we're going to show on the next page, we're going to call the analyte of interest X. This will all make sense when we see the form for writing Kovat's retention index. So the Kovacs retention index is abbreviated with a capital I. We're going to say capital I is equal to 100 times n in our previous example. If you rewind the video and go back and look, that's 10, right? That the value of that n is 10, plus this quantity, which is the log of the retention time of our analyte of interest x minus the log of the retention time of our leading peak n. That whole thing divided by log of the retention time of our trailing peak n plus 1 minus log of the retention time of our leading peak n. So basically what we're doing is we're making this numerical factor that describes retention time of x as its spacing between, so the log of retention time of x expressed in terms of its spacing between n plus 1 and n. This gives us this terminology, or this factor rather, Kovacs retention index factor. And this is useful for a bunch of reasons, actually. It's great for, so first of all, what is it? It describes retention independent of a lot of instrumental variables. So good examples, this value will stay constant regardless of what your mobile phase flow rate is, right? It's insensitive to flow rate. It's insensitive to column length. It's insensitive to a lot of other factors that influence the absolute time that this thing comes out, but will also influence the absolute time that all of these other standards come out. So we just define basically how it's bracketed relative to those standards. It's useful for, useful for evaluating columns and also methods, and for transferring methods between labs or from one instrument to another. But the reason we're talking about it today is that it's especially useful for comparing stationary phase materials. There we go, stationary phase materials. So in order to understand that, what we have to do is we have to introduce another new concept. It's a concept that uses this factor, this retention factor. So this concept is called McReynolds constants. So McReynolds constants are a list of numbers that do a lot to describe the intermolecular forces that happen on a stationary phase material. And if you go to buy a new column, you're going to have access to literature. In fact, I'll post in this discussion topic for this lecture, I'll post a link to a product material that shows a bunch of different stationary phase column options and what all of their relative McReynolds constants are. But basically it answers the question, how polar is this stationary phase? And of course, by polar, what we're saying is, how strong are the intermolecular forces? Right? The stronger the forces, the more overall polar the stationary phases. And we're going to do this, we're going to quantify this by comparison, right? By comparison to a very non-polar stationary phase, and that very non-polar stationary phase is squalane. So remember we said squalane is a C30 saturated hydrocarbon. The only intermolecular forces squalane is applying to analytes that pass over at our van der Waals interaction. So we're going to basically call this as nonpolar as it gets. So in order to get these McReynolds constants, we are going to consider 5 different model analytes. So McReynolds constants consider these 5 model analytes. The first one is benzene. And benzene is chosen because it's a nice model for induced dipoles. So if your stationary phase material can induce a dipole, it's going to do it on those nice mobile pi electrons that live in the benzene. So induced dipole, we're going to give this an abbreviation X. This X will make sense in a minute. The second model analyte is N-butanol. And this is meant to model hydrogen bonding, specifically as a donor. Right? So the hydrogen in that butanol can donate a hydrogen bond to some hydrogen bond acceptor on the stationary phase, and so it's a good model for that. Here's 3. Model analyte 3 is nitropropane. And it is meant as one example of dipole-dipole interactions. Dipole-dipole, there we go. Interactions, we're going to abbreviate that Z. 4 is pyridine. This is meant to model hydrogen bonding as an acceptor. So it can accept the hydrogen bond from some stationary phase material. We're going to call that U. And the last one, 5, is 2-pentanone. And this is just another dimension of modeling dipole interactions, and we're going to abbreviate that S. Okay, so in order to get McReynolds number, the first thing you're going to do is you're going to measure Kovacs retention indices. We're going to measure I for each on some stationary phase that we're interested in characterizing. Okay, so we're going to measure Kovacs retention index for each of these 5 things on some stationary phase of interest, and that's going to give us numbers that we call X, Y, Z, U, and S. Right, so these represent the I measurements for each of these 5 things on our stationary phase of interest. The second thing we're going to do is we're going to measure the same. Right, we're going to measure X through S on squalane. The good news is this is pretty well known, right? I mean, the idea of Kovacs retention index is to get this number that's independent of your instrument. And so this is literally something you don't actually have to measure. You can look this up in a table. Okay, so our McReynolds numbers are not these X, Y, Z, U, S. They're a modification of these X, Y, Z, U, S. They come from, so we're going to say X prime, that's our McReynolds number X, is equal to the X that we measured in our mobile phase of interest, right? The mobile phase that we're trying to characterize. And we're going to subtract from that the X measured on squalane. And that gives us X prime. And in the same way, we can get Y prime, Z prime, U prime, and S prime. And so the idea is to say, how much extra retention do we see compared to squalane for each of these model analytes, and that will tell us how much of each of these characteristic forces are happening on our analytes of interest. Um, so let's look at let's kind of throw together a table here of what this might look like. I'm going to throw this table over here because I think there's room. So here's a stationary phase of interest. Let's start with squalane, and we're going to look at our x prime, y prime, z prime, u prime, and s prime numbers. You know what? Here's what I'm going to do. I'm actually going to start this on a new page. Let's go onto a new page here. Let's set that up again. Here's our stationary phase, x prime, y prime, z prime, u prime, and s prime for squalene. Well, by definition, because we're subtracting uh, x of squalane, these are all going to come up as 0, right? This is essentially our prototypical non-polar stationary phase. It essentially models none of these, or at least by this mathematics, it models none of these interactions that we're interested in. If we look at something like OV1, really common, that's just PDMS inside a capillary tube. Here's some example numbers that we see. This is pulled straight from Sapelco. Probably the same thing I'm going to link to this link to in this discussion. 65 and 42. So this was PDMS. Here's OV17. This is the thing that's 50% PDMS and 50% cyano, right? 50% of the R groups are CH3, 50% are cyano. That cyano is a lot more strongly polar, and so it models a lot of these forces a lot more effectively. 158, 162, 243, and 202. Okay, let's do one more. Carbowax. And I don't know, I'm pulling these numbers from some old notes, so actually I don't know which version of carbowax this is, but it stands to reason if you look at those structures, it's even more polar than the cyano. So we see numbers like 322, 536, 368, 572, and 510. Okay, so there's one more number that you should know about, and that is if we average for any given stationary phase, if we average x prime through s prime, just add them all together, divide by 5, we get something that is called polarity, or P. So we can add a new column here, P. Obviously, the average of all those is 0. Here we get 44, 177, and 462. The thing with P is that it's a nice qualitative way of just one number that compares stationary phases, but in my opinion, and I think in a lot of other folks' opinions, the individual numbers are a lot more useful actually because they're modeling different things and they're not, averaging them together doesn't tell you the whole story, right? So this was, its ability to induce a dipole. It's clearly much less than its ability to accept hydrogen bonding, which I think was what our Y prime was. And so this is kind of a simple rule of thumb polarity comparison. In my opinion, I'm going to recommend that factors x prime through s prime are more useful independently, right? They allow you to actually design your method or your stationary phase selection a little more effectively for a specific interaction you're trying to promote. Okay, last thing we'll say on this whole thing, because it's a question that jumps into my mind every time I think about this, is why don't we do this in liquid chromatography, right? Why haven't we talked about some big retention index method for liquid chromatography? The first thing I'll tell you is some people do. There are some types of retention indices that can be used to compare retention and can be used to compare stationary phases in liquid chromatography. It's just not that effective, and it's not that effective for a couple of reasons. The first is that selectivity in GC is only about the stationary phase, whereas in LC, the mobile phase is just as important. And that means there are just too many possible combinations of mobile phase and stationary phase to characterize in this way. It's too complex of a problem to tackle in a universalized way in liquid chromatography. The second is that column variability in LC, sorry, it looks like I'm saying CC, in LC is a challenge. So although you may have the same stationary phase chemistry between two columns, say for example, the yield in functionalizing those surfaces will be different from batch to batch or from manufacturer to manufacturer, and therefore you're going to get varying degrees of adsorption or non-specific interactions on the stationary phase. Okay, this kind of begs the question though, and it's the thing we're going to talk about in the next video. If column variability is a problem in LC, but we're saying it's not that big of a problem in GC, well, what's the factor there, right? How are these columns put together in GC that allow us to get around in many cases this particular challenge? And so the next video is going to deal with the structure and construction of an LC, sorry, of a GC column.